Ladies and gentlemen, good morning. It's a privilege and an honor to be here once again. After 2017, it's my second time here in Bled, and I would like to congratulate Slovenko Henigman for this very nice conference. And we enjoyed already a lot, especially the evening yesterday. So I would like to talk about testing and testing equipment and testing procedures, because this is one of our major issues which is addressed at our institute in Braunschweig since decades, I would say. Also former colleagues addressed performance testing of asphalt mixtures and asphalt binders. And that's why I would like to talk about recent developments at our institute and the plan, how to proceed, how to go on, how to push the system forward of testing. And I would also like to acknowledge my co-authors, two young, very ambitious guys at my institute, doctor students, Johannes Büchner and Thilo Hilmer. And I would like to acknowledge a research fund program, which is a program within the German-speaking European countries, Austria, Switzerland and Germany. And I would like to acknowledge these institutes like ASFINAG, like Astra in Switzerland, and like BAST in Germany for financing parts of our study. So this is the outline of my presentation. I would like to talk a little bit on asphalt mixture performance testing, which has been developed for maybe 5 decades and became a really very important research tool. So when we develop asphalt mixtures using new additives, we try to simulate as best as we can in the laboratory real conditions and try to find out which mixture is the best. And it's a nice tool. And especially when we use complex asphalt binders, it's a tool which we cannot miss today. Second point is then why we focus today on asphalt mastic testing. Why we try to limit our testing efforts to very small samples, disregarding the nature of the complex nature and complex performance material behavior of asphalt mixtures, and what is the basic concept and how we are doing this. And I would like to present very shortly the dynamic shear rheometer, which is a basic test equipment to do asphalt mastic testing. Then I would like to shortly report on a laboratory program which has been performed for the last 2 years at TU Braunschweig and latest results. And then I will come to my main conclusion of this presentation. So first point, performance testing of asphalt mixtures means that we try to simulate what is happening in the road using asphalt mixture beams or asphalt mixture cores from the road or produced in the laboratory with laboratory mixing and compacting equipment. And as you can see on this slide, on this slide, which shows some examples, the world of asphalt mix testing is rather complex. We use different techniques and we use different specimen shapes and geometries, and also very complex shapes like, for instance, the 2-point bending beam, which is really tricky to produce. And this set of experiments is rather well developed, because the development started already maybe 50 years ago, and significant contributions also came from former colleagues of my institute, and they tried hard to put together a set of testing equipment which is nice and which can predict performance of the road already by testing the materials in the laboratory. Even though this is a nice tool, there are some still knowledge gaps to fill because, for instance, normative regulations, they are not precise enough to guarantee that all laboratories get the same results. For example, when it comes to fatigue testing, there can be differences among laboratories by more than 100%. So we have troubles. Another example why there are still gaps to fill is that the results are affected by the testing conditions, by the geometry of the test specimen, by the shape of the test specimen, by the magnitude. There is a size factor which is not considered. And we try to separate homogeneous from non-homogeneous tests to make at least a rough distinction of tests. We ignore more or less that the samples are not homogeneous. And this homogeneity is insufficient and leads to rather big scatter in the results. So this is mostly neglected, even though we know about these influences. And in the end, because the tests are rather complex and elaborate, we just do a limited number of tests for any material, maybe 3, 5, 10 samples, but that's it. And so the statistical database is not enough to derive really solid and sound results. So there are a lot of things more to do to make this this way of testing asphalt mixtures better. So, presentation doesn't work. Now it comes. We feel in Braunschweig that this test equipment is too elaborate for routine testing, and we see that we need rather complex instruments. We need academic staff to interpret the data and to interpret the data correctly, because you have to know about viscoelastic and viscoelastoplastic material behavior to interpret the data correctly. This is nothing for, not work for standard laboratory technicians. You need academic people. And the tests are rather time-consuming and expensive. For instance, when we do mix optimization for a big project, a PPP project, it takes us a couple of weeks and it costs maybe 20,000 euro to really optimize a mix in the laboratory. So no wonder that the road industry prefers empirical parameters. They stick to needle penetration, to softening point, ring and ball, to volumetric parameters like compaction degree and void content. No wonder that the idea of performance testing is more or less not used in routine work, not for quality control, not for selection of material components and mix design. It's not appropriate for routine work. So the road industry sticks to traditional parameters. But the problem is that these parameters, such as needle penetration and softening point ring and ball, were derived for plane binders, and they work for plane binders only. For modified binders, they do not work anymore properly. They are unsuitable for modified binders, and we see the difficult results, or difficult to interpret, as, for instance, regards polymer modified binders and the softening point ring and ball. So there is a problem with these traditional parameters, and I see that the problem is increasing because we are using more and more complex binders. We are not using plain binders more or less anymore, because we are using modified binders, polymer modified binders. This has become the usual way to do it. We are using viscosity changing additives to a high amount in Germany. We are using rejuvenators when we do recycling. So we are using not only fresh binders, we are using chemical products. And in some regions, like in northern Germany, we are already at the starting point of the second generation of recycling of asphalt. So the material is really highly modified. And of course, there you can observe changes on the bitumen market in the last 10, 15 years. So we need, as we see things in Braunschweig, we need a new asphalt specification system, and it should be based on rheological performance parameters. That would be really nice. So no longer needle penetration and softening point. We need solid parameters which are also working for modified binders. And our first approach to this problem was more or less the development of the binder fast characterization test, which was presented 2 years ago, also here in Bled. And this is the first step, which is a nice parameter to check the quality of bitumen and the performance of bitumen in the moderate and high temperature range. So what about asphalt mixture specification? How can we predict asphalt mixture properties in the laboratory by at low cost and at low time? So for asphalt mixture specification, there is a need of easy-to-handle performance tests, which are also suitable in routine testing, for routine testing purposes, which give robust and significant results at low cost, low time, and with reduced test equipment. So there is lacking something. There is a lack of practical tools. And such a practical tool, as soon as it is developed, could be used for a lot of purposes, like material control. When asphalt binder is delivered to the asphalt mix plan, we would like to have a simple, quick, cheap, rheological test of data, just to check the quality. Or when the asphalt mixture is delivered to the construction site, there should be a quick check at the construction site possible, or in the laboratory near to the construction site. So there is a lot of ways to use then such a practical tool. So our idea is to focus on asphalt mastic testing, which follows the basic concept of a multi-scale model, which means that the properties of an asphalt pavement can be considered as a multi-scale problem, which means that performance of asphalt pavements is already mirrored at lower scales, which means that we could do binder scale testing or even better mastic scale testing to predict important performance, key performance parameters of the asphalt mixture already at this lower scale. Now you would say, how can I predict asphalt mix performance from binder testing? It's impossible because there is volumetric consideration, there is aggregate skeleton and so on. Of course you are right, but what is important is if we fix parameters of our asphalt materials, and we follow the concept which we have followed so far with standardized materials, where the grading is standardized, the binder content is standardized, and so on. Then we are already in a very narrow, sharp concept. And within this concept, it's possible to predict performance of such materials already at a lower scale. So we are not ignoring volumetric properties, but we are considering them because we are sticking to an empirical volumetric concept. So how are these scales linked? And there is already some publications on links in the linear viscoelastic domain of material behavior. What means linear viscoelastic? This is a very small of material behavior, which is considered to be to show linear performance behavior, linear elastic and linear viscoelastic, where the derivation of strain is linearly depending on the stress. So for this linear viscoelastic domain, there is a very clear link of the scales. And so we can predict easily within the linear viscoelastic domain the properties of an asphalt mixture from binder testing. As you see on the figure to the right, there is a link which is shown here as a vector, but this vector has a mathematical background, and you can link all the scales by 2S to B1D model, which has been presented some years ago by the group of Hervé de Benedetto from University of Lyon. So there is already a link. But what is linear viscoelastic domain in practical terms? This is a domain where strain is really small. Let's say for asphalt mixture, you have a strain of maybe 10 to the power of -4. So 10 to the power of -4 means if you have it's 0.0001 meter per meter in the unit of strain, for instance. So if you have a beam of a thickness of 1 meter, which is just to give you an example, if you have such a thick beam and you bend this beam, you see a strain of 10 to the power of -4 means 0.1 millimeter. So it's a very small strain. So what about when we leave this linear viscoelastic domain? Then we come to all the properties which are more or less most interested in. So we try to focus on mastic testing also in the domain which is leaving the linear viscoelastic domain. And we do this by mastic testing and not by binder testing, because we learned from previous studies that there is a big influence, or there could be a big influence of the filler and the filler bitumen combination on the performance properties of asphalt mixtures. So it is more close to reality if we consider performance of the mastic than performance of the bitumen itself. And you can combine, let's say, a bitumen of poor performance properties with the right filler, and you will get very nice performance properties, and the other way around as well. So it's good to consider this interaction of bitumen with filler. So a lot of researchers started to study asphalt mastic properties, and most of them use the DSR. And the DSR in oscillating mode, so there are different equipments you can use as considers the DSR, and most promising technique, I would say, is the oscillating mode within the DSR, which you can see here on the figure. So what did we as a laboratory program at TU Braunschweig? We studied DSR. We studied asphalt mastic properties with the DSR in the linear viscoelastic domain, which means stiffness properties, here considered as the shear modulus, but also behavior in failure modes already, which means fatigue and low temperature cracking and permanent deformation. So we tried to cover the full temperature range in service, which means temperatures from -30 to +90 degrees Celsius. And we developed for all these three temperature ranges DSR tests for the individual temperature range. It's not true what I said, actually, because in the high temperature range the test was already here, so we picked it up. But in the low temperature range we could not find anything suitable, so we developed our own relaxation test and the fatigue test as well. So here are the specifications of the tests we choose. So it's a different geometry and slightly different test parameters for every temperature range. I will not go into detail because for reasons of time. So, but if you have any questions concerning these specifications, then please contact us, we will give you more information. The idea was now to look if our selected tests and the test specifications work properly. And there's a simple way to check if these tests work properly. They work properly if they predict typical performance parameters in the same way as they are found at the asphalt mix scale. Then the test works properly. So whenever researchers develop any new test, you should ask, is there a correlation of, a nice correlation, a good correlation of the low scale to the asphalt mix scale? So this is the big question we studied in Braunschweig for the last 2 years. And this is more or less the scheme of our work, that we looked at different temperature ranges and then at key performance parameters like cracking, fatigue, and permanent deformation. We selected performance tests at the asphalt mix scale, which was the tensile stress restraint specimen test in the low temperature area, then the uniaxial tension compression test in the moderate temperature range, and the cyclic compression test in the high temperature range. So we picked up known test procedures. They are nothing new. You can use them. They are all to be found in European or German standards. And then we compared the results with more or less the same idea of material testing, but at the asphalt mastic scale, tested with the DSR. So we in our study, sponsored within the program Vegas, within the German-speaking countries, we selected these materials. So we put together 18 different asphalt mixtures. We selected 2 different plain binders, 2 different polymer modified binders, 4 different manufacturers, and 3 different aggregate types for the coarse aggregate, and we added limestone as a filler. So here are the materials, and we produced the asphalt mixture, and we produced at the same time with the same ingredients asphalt mastic. So here you can see the results. First slide on the low temperature tests. So we found, as you can see here, a very nice correlation between stress relaxation at the asphalt mastic scale and stress relaxation in the low temperature test at the asphalt mix scale. And as you can see here, the population, the number of test examples is 77, and the coefficient of determination is slightly below 0.9. So it's a nice correlation, even if you consider that there is a rather big scatter in the results when you do performance testing at the asphalt mix scale, then this is really a nice correlation. So we can consider the test at the mastic scale at low temperatures, this relaxation test developed at our institute, is a nice way to predict low temperature behavior of the asphalt mix. So what about fatigue testing? Here you can see the results from these 18 asphalt mixtures and the corresponding asphalt mastic samples. And here the coefficient of determination is around 0.7, considering 337 pairs of test results. So the correlation is not bad, could be better. You can see some outliers shown here in red. So we are discussing at the institute, maybe there was something wrong at the asphalt mix scale. So we have to study that more in detail, and maybe the correlation becomes even better afterwards. We don't know yet. And the last point here are the results for the creep test. So to study performance behavior at high temperatures, and even here we find a very nice correlation. But I have to admit that the number of test samples is at the moment with a number of 63 limited, so there need to be more data. And this is a program we started in autumn this year for a couple of German companies, road constructing companies. We test their materials according to these test specifications. So we will have a lot of data within the next 2 years, which hopefully will support our basic concept of mastic testing. We will see. But in general, at the moment, we found out that the DSR results really look good at the mastic scale. They correlate quite well. So it is possible for standardized asphalt mixture to predict performance in the laboratory by very easy tests, because these tests, I think at the moment, the test which takes the most time is the creep test, and this is done within, I think, 90 minutes. So they are very fast. These tests are very fast. So main conclusion of this study is the more and more we see in Braunschweig that DSR testing is very nice technique, and the results, they mirror really very nice conventional tests at the binder scale. So we can replace penetration and ring and ball very nicely with DSR testing at the binder scale. We can also replace PBR tests at the binder and mastic scale by using the DSR. There is a PhD at my institute at the moment which shows this very well, that PBR can be replaced by DSR. And we try to also replace monotonic static TSRST tests and cyclic tests by studying asphalt mastic with the DSR. So that's for today. If you have any questions, I'm happy to answer. Thanks for listening.